Now let's look at the Lewis structure for covalent compounds. So covalent bonding is from the sharing of the electrons. So the valence electrons are being shared. For ionic bonding, valence electrons were being transferred, but for covalent bonding, valence electrons are being shared. Now the valence electrons for covalent bonding are going to be shared, and the goal is to achieve octet. Now there are a couple of exceptions from the octet rule. So we need octet rule for from the helium to basically neon. So for the elements in the period 1 and period 2, we're very strict with octet rule. Now the exception here is hydrogen. Hydrogen cannot have 8 valence electrons. Hydrogen follows the duet rule, meaning that the maximum number of electrons hydrogen atom can have is only 2 valence electrons. Now from period 3, we can exceed the octet rule, and I show you how that works. Now, in order to do Lewis structures, there are different methods that you can use in order to do Lewis structure. So I'll show you a method here. So we're gonna hear some rules and some steps, and I'll show you step by step how you can do the Lewis structure. Now, when we talk about sharing of the electrons, this is what I mean. Let's say you wanna look at the Lewis structure of the methane. So methane is composed of 1 carbon and 4 hydrogens. So carbon is in group 4A. It has 4 valence electrons. Each hydrogen has 1 valence electrons. So our goal in order to get carbon and hydrogen to bond is to share these valence electrons. And once you share the valence electrons, carbon needs to be octet and hydrogen needs to be duet. So whenever it's covalent bonding, meaning that the bond is in between 2 nonmetals, you're going to share the valence electrons. Now, carbon and hydrogen are going to share the valence electrons. And by sharing the valence electrons, CH4 is formed. Now, in the Lewis method, the interacting electrons, or the electrons that are being shared, are represented by a single line. So now if you look at carbon, carbon has 8 valence electrons, 8 electrons that's associated with it. Here is 2, 2, 2, and 2. So 8 valence electrons, and each hydrogen has 2 valence electrons associated with it. So each dash or single line represents a covalent bond in between 2 nonmetals, and each single line stands for 2 electrons, and those are basically bonding electrons. Now if we look at the CH4, duet and octet rule both are fulfilled. Carbon has 8 valence electrons and hydrogen has 2 valence electrons, so this is the perfect Lewis structure for CH4. Now some of these duet and octet rules, you know, they're followed in nature. Remember how we talked about diatomic molecules? So here is an example. You know, for the molecule of hydrogen, H2, it's composed of 2 hydrogens. Each hydrogen has 1 valence electron. So when they share this electron, H2 is formed. Same thing with fluorine. Each fluorine has 7 valence electrons. In order to be octet, each fluorine needs 1 more electron. So these fluorines are going to share those valence electrons, and they're going to form F2. So that's how these diatomic molecules are formed. H2 and 2, O2, Cl2, F2, Br2, and I2. Now for hydrogen, we have the duet rule, and for the rest of this, we have the octet rule to make them diatomic. Now let's look at the steps that we use in order to draw Lewis structure of covalent compounds. So let's say that you want to draw the Lewis structure for HOCl. Step 1 is counting the total number of valence electrons available. So what does that mean? The molecule that's given to us, HOCl, composed of hydrogen, oxygen, and chlorine. So hydrogen has 1 valence electron, oxygen 6 valence electrons, and chlorine has 7 valence electrons. So we have a total of 14 valence electrons. What this means is that we gotta use these 14 valence electrons, share them in a way that after we're done, oxygen is octet, chlorine is octet, and hydrogen is duet. And we have only 14 valence electrons available. Now step 2, you want to draw the skeleton structure for this molecule. Like the simplest way hydrogen, oxygen, chlorine could be connected. So in order to make this a molecule, hydrogen, oxygen, and chlorine needs to be bonded. So I use these single lines to connect hydrogen to oxygen and oxygen to chlorine. Remember that in the Lewis structure, each one of these single lines represent 2 electrons. So in a step 2, by just connecting hydrogen, oxygen, and chlorine, I used 4 electrons already. So 4 out of that 14. Now let's see how many electrons we have still available. So we used 2 electrons for each one of these single lines. We initially had 14 electrons, and 4 of them we used in order to make the skeleton in a step 2. So we have a total of 10 electrons still available. So we have 10 electrons available, but let's see how many electrons we need in order to complete this structure. So if you look at your skeleton, hydrogen doesn't need any electrons. It's already duet and it's complete and it's happy. However, oxygen still needs 4 more electrons to be octet. And chlorine needs 6 more electrons to be octet. So I still need 10 electrons in order to complete the octet of chlorine and oxygen. So 10 electrons are required. Now in step 5, we're going to subtract available minus required electrons. So available, you have it from step 3, 10 electrons. From step 4, you have required electrons. So if you do available minus required, you end up with 0. Now since it's a 0, it means that our structure, our Lewis structure, is a simple structure, and we only need to distribute the electrons on the elements to make them octet. I'll show you later on, if you don't end up with a 0, what we're gonna do. But since this is a 0, it means that we don't expect to see any double bond, extra lone pair, or anything. So we're gonna look at our skeleton from step 2, and we're going to distribute those 10 valence electrons we had available in order to make oxygen and chlorine octet. So 2 and 2, 4, 6, 8, and 10, and this is the Lewis structure of HOCl. Now, hydrogen is duet, oxygen is octet, chlorine is octet, and in total, we have used only 14 valence electrons. So let's look at another one. We want to draw the Lewis structure for nitrogen molecule, N2. So first step is counting the total number of valence electrons available. So N2 is composed of 2 nitrogen atoms. Each one of them has 5 valence electrons. So we have 10 total valence electrons. Now step 2, we want to do the skeleton for this molecule. So we're just going to connect the 2 nitrogens with a single bond. So step 3, you want to calculate the available electrons. So we started with 10 total valence electrons, but we used 2 electrons in order to make the skeleton for N2. So we have a total of 8 electrons available. Now, in step 4, we want to see how many electrons are required in order to complete the octet of each nitrogen. So looking at the skeleton in step 2, each nitrogen still needs 6 more electrons. So in total, we need 12 electrons in order to complete the octet of each nitrogen in our skeleton. Now in step 5, we're going to calculate available minus required, and if you do 8 minus 12, you're going to end up with a negative 4. Now in step 5, if you end up with a negative number, it means that you expect to see a double bond or a triple bond. You expect to see extra bonds. So it's negative 4, and each bond composed of 2 electrons, so that gives you 2 extra bonds. Now the 2 extra bonds go in between the 2 nitrogens. So here is one of them, and here is the other one. So that negative 4 means 2 extra bonds. Now, the nitrogens are still not octet. We still have 4 more electrons to use to make each one of these nitrogens octet. Now, this is our final Lewis structure. Each nitrogen is octet, and we have used only 10 valence electrons total. So for sulfur tetrafluoride, first we're going to count the total number of valence electrons. So sulfur is in group 6. It has 6 valence electrons. Fluorine is in group 7, 7 valence electrons. And we have 4 fluorines. So we expect a total of 34 valence electrons. Now step 2, we do the skeleton in between sulfur and fluorine and connect them with single lines. Now, since we're using electrons to make this a skeleton, we have to subtract those electrons from the initial 34 electrons that we had available. So now, after making the skeleton, we only have 26 electrons available. Now, in step 4, we're going to look at our skeleton from step 2 and see how many electrons we need in order to complete the octet of sulfur and each fluorine. So each fluorine still needs 6 more electrons to become octet, and sulfur is already octet. So we need 24 electrons in order to complete the octet of sulfur and each fluorine. Now, step 5, you calculate available minus required, and when you do that, you end up with positive 2. So when you end up with a positive number from step 5, it means that you expect lone pair on your central atom. And since it's 2, it means we need 2 extra electrons on the central atom, and those extra ones go only on the central atom. So each fluorine needs 6 more to become octet, but we need 1 extra lone pair, 2 electrons on the sulfur. And now this is the Lewis structure of sulfur tetrafluoride. Now, as you see here, sulfur in the final Lewis structure has 10 valence electrons, but this is totally okay. So from period 3, your central atom, and only the central atom, can exceed octet. The reason they can exceed octet is because from period 3 we have all the d orbitals available. So there is room around the central atom for extra electrons or extra bonds. And this is very, very strict to elements from period 3 and on. And again, keep in mind that only your central atom can exceed octet. So now let's look at resonance structures. So let's say you want to do the Lewis structure of ozone, which is O3, and following all the steps, we're gonna end up needing we're going to end up needing a double bond in between the oxygens. But if you look at the skeleton for oxygen, we don't really know where to put the double bond. Does the double bond go in between these 2 oxygens? Or does it go in between the second and third oxygen? So both are basically a possibility. And we don't really know where the double bond should go. So these are the same thing, because wherever you put the double bond, the Lewis structure looks the same. It's just that the location of the double bond, that's not the same. So these type of a structure are called resonance structures, and it appears that both are correct structure. The second bond, which is the double bond, is called a delocalized double bond, and we don't really know where it is, but each one of these structures is a possibility. So these are called resonance structure. Resonance structure is when you have a double bond that could be in different places in your structure, but keep in mind that for resonance structure, the final structure still look the same. It's just that the location of the double bond that is going to be different. So let's do a couple of examples. Let's start by the Lewis structure of carbon tetrachloride. So it is a covalent compound. So I would expect the valence electrons between carbon and chlorine to be shared. So first step, I'm going to count the total number of valence electrons. So carbon has 4 electrons, and we have 4 chlorine, each one of them 7. That's a total of 28. So we have a total of 32 valence electrons. Now I'm going to make the skeleton in between carbon and chlorines. And by doing that, I'm using electrons. So I had 32 total, and I used 8 of them to make the skeleton. So I still have 24 electrons available. Now let's see how many electrons are required to complete the octet of carbon and chlorine. So carbon is already octet. Each chlorine needs 6 electrons to become octet. So 24 electrons are required to complete the octet of chlorine, each chlorine and carbon. Now, if we do available minus required, we end up with 0. So I don't expect extra lone pairs, I don't expect double bond or triple bond. So I'm going to distribute the 24 electrons that I had on carbon and each chlorine to make each one of them octet. So carbon doesn't need more electrons, however, each chlorine needs 6 more. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Now, to check the structure, carbon is octet, each chlorine is octet, and I use 32 valence electrons total. So this is the Lewis structure of carbon tetrafluoride. So let's do the Lewis structure for carbon monoxide. So let's look at carbon monoxide. So first we want to count the total number of valence electrons. So we expect 4 valence electrons from carbon and 6 valence electrons from oxygen, a total of 10 valence electrons. Now we create the simple skeleton between carbon and oxygen, and by doing that I'm using 2 electrons. So now I only have 8 electrons available. Now, in order to make carbon octet and oxygen octet, I need 12 electrons. Because carbon needs 6 electrons, oxygen needs 6 electrons too. Now, if we do available minus required, we're gonna end up with -4. So -4, it means that first of all, the negative means that I would expect to see either a double bond or a triple bond, extra bonds. And now since it's a -4, I expect to see 2 extra bonds. Here they are. Now 2, 4, 6, and we still need 4 more electrons for carbon monoxide to make it octet. Now carbon is octet, oxygen is octet, and we have used only 10 total valence electrons. So this is the Lewis structure of carbon monoxide. Now, let's look at the Lewis structure of ammonium ion. So first, we want to count the total number of valence electrons. So for nitrogen, group 5, we have 5 electrons. We have 4 hydrogen, each one of them 1 electron. So 4 electrons. But we have a +1 charge here. +1 meaning losing 1 electron. So I'm taking 1 electron off just because that +1 charge. So that's a total of 8 valence electrons for ammonium ion. So since it was +1, I removed 1 electron. Now we do the structure, the skeleton between nitrogen and 4 hydrogens. And by doing this, let's see how many electrons we use. 2, 4, 6, 8. So we have 0 electrons available. Let's see how many electrons are required to make the octet. So nitrogen is octet and hydrogen is duet. So 0 electrons required. So if we do available minus required, that's also a 0. So 2, 4, 6, 8, I had 8 valence electrons available. Nitrogen is octet, hydrogen is duet, and in terms of electron, this is correct. But this does not represent ammonium ion, because we gotta show where the charge is. So for polyatomic ions or any ions in Lewis structure, remember you put brackets and you put the charge outside of the bracket. Now this represents the Lewis structure of ammonium ion. So let's look at the Lewis structure of a nitrate ion. So to draw the Lewis structure of nitrate ion, we first have to count the total number of valence electrons. So nitrogen in group 5, 5 electrons. Oxygen is in group 6, and we have 3 of them. So we would expect a total of 18 electrons from 3 oxygens. Now the charge on the nitrate ion is a -1. Negative meaning electron was gained. So I'm going to add 1 electron because of the -1 charge. And that gives me 24 electrons total. Now, we're gonna do the simple skeleton between nitrogen and oxygen. And by doing this, so I started with 24 electrons, and I used 6 electrons to make this skeleton. That means I still have 18 electrons available. But let's see how many electrons are required to complete the octet. So for nitrogen, we need 2. Each oxygen needs 6. So it means 20 electrons are required to complete the octet of the skeleton I made. Now if we do available minus required, that gives me a -2. -2 meaning that I need 1 extra bond. Here is that 1 extra bond. Now we gotta complete the octet of nitrogen and each oxygen. So nitrogen 2, 4, 6, 8 is already octet. Now here, once you're done with this structure, you should have a total of 24 electrons. So we count them: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So those are the 24 electrons that I had available. Now, this is not the correct structure because the nitrate ion has a -1 charge here. Now, for this structure, we would expect resonance structure because this double bond could be with any of the oxygens. So I could technically put the double bond here, and this is still the correct structure for a nitrate ion. Or I could put the double bond here. And these structures are all the same. So these are all resonance structures for the nitrate ion. How do I show that these are resonance structure? This is the symbol you use for resonance structures. So let's do the Lewis structure of xenon tetrafluoride. So first, we're going to have to count the total number of valence electrons. So xenon has 8 valence electrons. Each fluorine 7, and we have 4 of them. So that's a total of 28 electrons from fluorines. So we would expect 36 electrons total. So I'm going to make the skeleton here. (36 minus 8 electrons). So we have 28 electrons available. Now to complete the octet for this skeleton, xenon is already octet, but we need 6 electrons for each fluorine. So we need 24 electrons to complete the octet. Now if we do available minus required, that gives you 4 electrons. So 4 electrons, meaning that I would expect extra pairs of electrons, lone pair of electrons on the central atom. Here is the 4. So 2 and 2, 4 of them. Now, we have 36 electrons total, and we have already used 12. Now, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Now, each fluorine is octet. Xenon has exceeded octet, but it's okay. Xenon is in period 5, so it can exceed octet. And we have used 36 electrons total. So this is the Lewis structure of xenon tetrafluoride.